again, I'm gonna like do a song and dance and allow more people to arrive. But because there are a total of 3 carbons in here, and it's a ring, this guy is gonna be called a cyclopropane. And the square is your cyclobutane. And the 5-membered ring will be the cyclopentane. The 6-membered ring will be the cyclohexane. And the 7-membered ring will be the cyclopentane. But each of them will have its own uniqueness that we want to actually look at, okay? So when I start with the cyclopropane is planar. Cyclopropane is planar. And we represent those hydrogens up and down, right? We represent the hydrogens up and down. And I think I gave an example of that. We start introducing one more strain, okay? I think when we were looking at the conformations of butane, we had talked about a torsional strain. Does anybody remember what was the torsional strain? What was the torsional strain? Anybody?
When you have 2 groups interfering with each other.
When you have 2 groups kind of like behind each other, so you have to have adjacent carbon, carbon 1 and carbon 2, and all the attachments on carbon 1 is all exactly behind the attachments of carbon 2, and that was eclipsed. Okay, to keep that in that situation, like in your face, that was in your face. To take that away, you rotate, and that was a staggered, which is not in your face. Okay, so that's a relieving torsional strain. So torsional is staggered and eclipsed. When you are in my face, and then you are in my space, that was called a steric strain. You're in my face, and in my space, that's your steric strain. And we're going to take a look at another strain, which is going to be called the ring strain. The ring strain refers to forcing a carbon that is sp3 hybridized, that wants to be at a 109.7 or 109.5 degree angle to conform with a smaller angle. That's called a ring strain, okay? So the more you are forced to be less than 109, the higher your ring strain. And we're going to take a look at that and see how we're going to play that. We're going to remember it in an easier way. When I start rotating my cyclopropane, take a look at what happens when I rotate. Did you see what happened? I'll come back. See what happens when I rotate the cyclopropane. What has happened? They are eclipsing one another. It's everybody. So not only does the cyclopropane have this torsional strain, the cyclopropane also has what we call that eclipse, which is the torsional strain. So cyclopropane has the ring strain, and it also has that torsional strain. I think what we did for this was naming, right? We did this one was naming, and I think we said if you looked at dichlorocyclopropanes, I'm moving back to here. May I switch over here? So if we come over here, for people that are just arriving, we are still having the test on Wednesday, September 23rd. We'll include chapters 1 through 4. We have 2 more labs on Monday the 14th and the 21st. We will do discussions there, not here, so that I can finish all that I need to do to cover. 4 more lectures before the test arrives. So if they're asking you to draw as many isomers of dichlorocyclopropanes. Oh my gosh, the handwriting, look at that. Draw as many isomers of dichlorocyclopropanes as possible. Where do we begin, right? Where do we begin? Good morning. Where do we start?
The cyclopropane.
With the cyclopropanes? Oh, this little is too small. All right, so usually I want to go ahead and start out like this. And I can start out with them being on the 1,1. that makes sense, that I would have the 1,1-dichlorocyclopropane. Or it makes sense that I can do the 1,2-dichlorocyclopropane. Do I have a 1,3? No, because it will be 1,2, right? So these two, oh, I did such a good job yesterday. These two are called what? These two are gonna be called, so this is your 1,1, and this is dichloro, and this is gonna be 1,2, dichloro, and both of them are cyclopropane, right? That will be the name. 1,2, and this one is also 1,1-dichlorocyclopropane. If somebody said, what is the relationship between these two? These two are said to be constitutional isomers. So they're called constitutional isomers. Somebody else can call them structural isomers. Structural, yes, you. Structural isomers is an old term. It still can be, go ahead and use. Or I can come over here and draw these guys, kind of like your MTV, that I can either have these chlorines both on the same side, as you. Take a look that if you had to name the compounds, this is a 1,2-dichloro, and this is also a 1,2-dichloro. So the names are the same. They're both gonna be called 1,2-dichlorocyclopropanes. Already not a constitutional isomer. Constitutional isomers have different connectivity, 1,1 versus 1,2. When you have the same connectivity, 1,2 and 1,2, but the orientation is different, right? The orientation is different, then that in 3D is called a stereoisomer. Stereoisomer, a chapter 5. Stereoisomers. This is chapter 5. In your chapters 2, 3, these guys are called geometric isomers. So you have to know both names. In order for your compounds to be named correctly, the orientation when they're both pointing to the same side, this will have to be called cis 1,2-dichlorocyclopropane for this. Right, this one will be called your cis 1,2-dichlorocyclopropane. And this one would have to be called trans 1,2-dichlorocyclopropane. Is everybody okay? And that terminology we're gonna keep using through the whole entire chapter. All right? Everybody okay? Any questions? Yes?
So can you use stereoisomer and geometric isomer kind of interchangeably?
Well, we are right now, but not later. Okay, so geometric isomers, biologists don't want to get away from that. So a geometric isomer is a really old nomenclature. It's really in reference to where they are. We organic chemists are going to call them stereoisomers. Okay, so you can call them now stereoisomers if you want. But if you see geometric isomer in multiple choice, obviously go for that one. Okay. All right, we continue on. I'll switch you out. We continue on, and then we're going to go to cyclobutane. Cyclobutane is really drawn more like a trapezoid type thing. I really draw it as a square because I'm not going to be able to draw that and make any kind of sense. The structure is said to be puckered. It's the only time that the word puckered appears in the whole entire book. I don't even think it appears in the weight textbook. But take a look at the ring strain, a little better. Did you see? It's a little better. The other one was 28 kilocalories per mole. Now we have 27. and I'm not gonna remember those numbers, but take a look as when we rotate. Is everybody able to look when we rotate? Can you see when I'm gonna rotate? And I stay there, you see between these two carbons, focus on these two carbons. Is this eclipsed? No, because you see it. Is it staggered? Well, no, because staggered is 60 degrees. So eclipse is right behind you, staggered is 60 degrees. When it's somewhere in between, it is not 0 or 60, that terminology is said to be skewed. Like the skewers on your barbecue when you do shish kebab is called skewed. Okay, the term is skewed. I don't know if they're gonna write the word there or something. Let's take a look. Can you please stop doing that? Skewed. So that is the term called when you are not at 0, eclipse, not at 60, which is staggered, but now you are skewed. Probably anything less than 60. And it depends on the structure, so it's less than 60. We know that the cyclobutane does the little birding flight. So that is your cyclobutane. Oh, I was enjoying it. All right, and now we go to cyclopentane. I cannot draw in the envelope or the chair. Is everybody? So I cannot draw either one of them, neither one of them. Neither one of them I can draw. And so because I cannot draw neither one of them, I am gonna say that my cyclopentane is really, really gonna be a beautiful, beautiful flat surface of a pentagon. So let me switch us back. Ring straight better about 7. Are you ready? Okay, following the same mentality and this time allowing you to work. Draw all possible, following the same mentality. Draw all possible. Oops. Draw all possible dibromocyclopentenes. Draw all possible dibromocyclopentane. Molecular formula C5H8Br2, and see how many can you come up with, okay? You see how many you can come up with, and then I'm gonna play. So you see how many you can come up, and then I play. Okay, so I don't know how many have you drawn, but I'm gonna draw 2. I hope you allow me to draw. Okay. I have my little template so I can go really fast and not sloppy. Alright, so I have those 3 there, and I have this. Okay, and I think there are many things in your book that ask you what is the relationship between these 3. I hope everybody knows how to name them, right? This is going to be your 1,1. This is going to be your 1,2, this is going to be your 1,3, and everybody knows there's dibromo cyclopentane, and you would have multiple choice, right? Are these geometric isomer A? Are they the same, identical? What are they? These guys are constitutional isomers, right? Constitutional isomers. It's a good idea. Somebody said, wow, you really teach this class very systematic. We're highly organized in our own heads, okay? We're highly organized in our own heads. So So this is good, but what if I do this? What if now I say, what is the relationship between these and these? So I'm gonna draw them. So what is the relationship between these two?
Stereo.
They stereo, constitutional,
Stereoisomer.
what did you say?
Constitutional,
How do you know? He said they're constitutional. How do you know?
because they're on a different carbon atom.
They're different connectivity, don't let me fool you. The first thing you're gonna do is name. When you name, this is 1, 2. Okay, yeah, this is cis 1, 2, right? And this is 1, 3. And this is trans 1, 3. To be geometric, you have to have the same connectivity. If they're in different places, a 1, 2 and a 1, 3, these guys are constitutional. It doesn't matter that you're cis and trans at this moment. What matters is the connectivity. These guys are still constitutional isomers. You are so mean. Okay, I disclose everything before the test. You want to make sure that you don't make this terrible mistake, all right? And then, of course, we go to the next one. And the next one goes without saying that we'll come over here, right? So we'll come over here, we'll draw 2 more. And when I draw this 2 more, and I'll put my, I'll put a BR here, and a BR here, I'll put a BR here, and a BR here, okay? Take a look that they are the same connectivity. So the first thing that you're going to do in order to decide, are these guys the same or different, right? First thing you look for, are they the same? Because, you know, we can put both structures to be identical. I mean, I can turn these things around and they look like 2 different things. So then the next thing you're looking for is the name. This is a 1, 2, and this is a 1, 2. So when the bromos are both in 1, 2, are they oriented in the same direction? They're both to the front, or one is to the front and to the back. Now when they're both 1, 2, when they're both 1, 2, and this is the cis 1, 2, and this is your trans 1, 2, now is that you call these guys your geometric isomers, right? At this moment is that you're calling them the geometric isomers. All right, stereoisomers for your test 2. So how many were there? How many isomers were there? Draw all the possibles. How many were there? If this is a multiple choice, how many were there? Somebody said? 7? 7? Bless you. I don't know.
5. We're including front and back.
So far, right now, the front and back counts as 1. So if they're both to the front and both to the back, that counts as 1. So both to the front, both to the back is 1. So we have the 1, 1, the cis and trans 1, 2, and we have the cis and trans 1, 3 for this test. So for this test, we have 5. When we add stereoisomers, we probably have 7. So whoever said 7, you are right. But so if you see, here we go again. If you see A, B, C, and D, right, and you have 2, 3, 4, 5, hey, pick the 5 and don't sweat it, right? Even if you see 7, don't argue with the test. Just 5 is what you have drawn. We're going to have another stereoisomer. People get really stuck. Oh my God, but I see 7. Well, if 5 is the larger number, just, you know, accept that one. Don't go crazy. All right. So let's go back where we were. And that was my cyclopentane, ring straight 7. When I continue on and I take a look at the carbons. Oops, back again. Did you see where we are? The only thing I see is like right here. back again skewed. We're still not staggered, everybody. Back again skewed. So remember, once you get to staggered, that's gonna be the most stable ring, right? The most stable ring. So now we're at 7. We go to the next one. Okay, let me go. Here's the cyclohexane. Cyclohexane, okay, the ring strain is about 1 kilocalorie. Again, I'm not gonna memorize this. I'm gonna tell you how I'm gonna use all that. When I go ahead and I rotate the ring, are you looking? Okay, look at your chair. Ooh, they didn't let me rotate the ring. Look how the chairs go back and forth. We're gonna be able to draw them soon. And the very last one is your cyclohexane. So, before we get any further than this, if you go ahead, have you noticed that every time you call, I mean, some people said, how was your weekend? Somebody asked, how was your weekend? And I really have to say my weekend was extremely stressful. I got home Friday after doing a lot of stuff at home, and I open the mail and I get a bill from UCSF for $100,474, which I almost flipped out. I have evidence because I don't want you to think that I'm just insane. So I have evidence of what that was, and I went, oh my God, oh my God, oh my God. Of course, you cannot solve anything. So there's the evidence of my bill. Did you see the numbers? 100,474.52. I thought I was going to collapse. It's like, how is this possible? How is this possible? Yeah. I spent most of Saturday crying. It's like, who am I going to ask to borrow that money? Because it's like, hello, you know, we all teach here. So you call, nobody could answer. Anyway, yesterday I was able to get the whole conversation. It really just turned out to be only $250 instead of this whole thing. But it put my nerves, destroy. Where was this story going? There was a reason for the story. I totally lost it when I thought of the cycloheptane. There you go. Thank you. Like, there was a reason for this. You can see how my weekend was. I mean, all I've done is cry Saturday and Sunday. It's like, oh my God. All right, so usually when I call and start arguing, the first thing she goes, well, what's your name? What's your zip code? Right? I mean, that's, even when you're putting your money to get your gas, they want to know what's the zip code, right? So the zip code has become. So the zip code idea really works for me with these rings, okay? The zip code idea really works well for me with this ring. So this is my ring strain stability. 6, 5, 7, 4, 3. That's the ring stability. 6 the most stable, 5, 7, 4, 3. You're gonna remember that forever. 6, 5, 7, 4, 3. The most stable ring is a 6-membered ring, followed by the 5, then the 7, the 4, and the 3. So 6, 5, 7, 4, 3 is the ring stability. And that's all I'm going to remember. There is a part that you're going to use this information in your discussion packet where they're really asking you which one is the most stable. And that ring strain, the ring strain, is strictly in reference to a carbon that is sp3 hybridized, made to conform away from its normal 109.5 degree. Okay, so that's really what it's asking. I'm going to start drawing for the bicyclos because I don't think they do as good a job as I do. So I want to draw bicyclos for a moment. And we have to learn how to name them. Bicyclos, well, the name already says it all. So bicyclic compounds kind of look like this, okay? They can be fused. That means that one carbon, right? So we have one ring, and then we can attach another ring to it. That is called a bicyclo, and this is called fused. fuse means that two carbons are sharing, can you see these two carbons? Are sharing the connectivity. Okay, these two carbons that are sharing that get a special name, okay? And that special name is called the bridge head carbons. Okay, that's the bridge head carbon. The bridge head carbon says, I am holding the structure, okay? I am holding on to the whole structure. And the way that we name these compounds is the first thing is that you recognize that it's a bicyclo, so you call it bicyclo. Now, we put brackets, and brackets say, you know, I'm gonna go from here to here in 3 different ways, okay? I can either go orange this way, that way, I can go that way, or I can go this way, right? And either way is the same. And I know that in order for me to get from here to there, I'm gonna have to hop through 1, through 2, through 3 carbons. I'm hopping through 3. And if I have to go from here to here, I can go this way, or I can go that way, and I will be hopping through 1, through 2, and 3 carbons, or I can just do the slide. Is everybody? So the name says you're gonna do your hops in a descending order, and you're gonna separate the numbers now with little periods or dots. And so this compound is gonna be called bicyclo 330, and then the total number of carbons, there are, well, there's 6, right? Already there are 6 and 2 more, but you know that there were 5, 6, 7, 8, so this will be called a bicyclo 330 octane. Let's try another one. The 0 is the slide. I didn't hop through any carbon, I just did a slide. There wasn't any hop. So everybody, if you don't hop, it's a 0, which is the slide. Anybody can do bicyclos. Look how simple this is. This is my favorite bicyclo. My favorite bicyclo looks like this. My little cupcake. My little cupcake is a bicyclo. And would you be able to name it? Sure. I'm gonna help you out. I'm gonna call it bicyclo. I'm gonna help you out with the brackets. And then, can you label the bridgehead carbons? But yeah, you're right here. So there's 1 and there's 2. Those are your bridgehead carbons. Remember, the story is that you go in descending order. Descending order. And so I'll mark them. And I can go from here to there through the little doughy part of my cupcake.
You said descending order, lowest,
Highest to lowest, yeah. Or I can go through the frosting. Or I can just take the frosting off, away. All right? So descending order will be a 2, a 1, a 0, and then pentane. Yeah? Is everybody okay? So we do one more? Let's do one more. Somebody says we don't even need to do one more, I get this, but I'm gonna do one more just for the fun of it. Oh. I did so much better before I started. Let's try that. You name it yourselves. This this happens. Okay. So, do we have a name?
421.
So she said, does this really happen? You know, frankly, this does happen, but oftentimes, even if it doesn't happen, all we have to do is name it, okay? So we're not gonna try to build it. Somebody said it's what?
421.
421, is everybody agreeing on 421? I see a lot of people saying yes, 421. And then no name? Yeah? Okay, there's a very typical bicyclo that we have to do. And this bicyclo that we have to memorize its common name. This bicyclo that looks like this. It's not drawn like this anymore. Bicyclo that looks like that is, what happened?
Is this supposed to be octane? It's got the center carbon.
So let's see,
Oh, never mind, yeah.
never mind.
Yeah.
Everybody okay that is no name? You had 8 to begin with. An easy way to do it is also this way. 4 and 2 is 6, and 1 is 7, and then the bridgehead carbon, so it's fine. Okay, this guy, that will be the same way that you've named that one before. On a test, it's not gonna look like that at all. This guy is not gonna look like that at all on a test. Let me show you how this is gonna look on a test. This is gonna be drawn like so in a 3-dimensional drawing. It's gonna go like this. If this is like if you had, like if you put together a 6-membered ring, you know, like flat on the table, and then you put a handle and you pulled up, right, and you pulled up. So it's gonna be drawn like that. This guy's name is called Norbornane. So this one is called Norbornane. You have to memorize this. How would you name it according to these bicyclo stories? How would you name it according to bicyclo stories?
221.
Okay, so then you would call this bicyclo. They're telling me 221. Is that right? 221. What else?
Heptane.
Heptane. Students do really well with the bicyclo nomenclature. We don't do substituted bicycles, bicyclos. You don't do any kind of, any other things. I wanna go ahead and switch us out. Oh, I cannot see here anything. I am very sorry, students. I cannot see anything here unless I look. All right, so we have that. Let me go, I don't wanna be here anymore. All right, so those were your monocyclic. We will only be responsible to drawing flat. The only one that we now have to draw is the chair. Okay, so I am going to say we're going to the very end of that. And we don't need to know that. We do the steroids when we do the sex lecture in Chem 4. But I'm coming over here. And, oh, I cannot even see anything. All right, we get to this one and let's start drawing that. We're gonna start drawing chairs. I don't know if I remember, I think I remember saying bring an red and green. Did I say that to this class? Bring a red pen and a green pen. I think I said that. Okay, let's take a look at our chairs. We'll take a look at our chairs and see what happens with our chairs. All right, so we begin like this with the cyclohexane. We start out like that with the cyclohexane, And then it looks like this, which is the chair conformation. And I'm gonna start to draw, because all of a sudden, when I turn, okay, so here we are with the chair conformation. Is everybody okay? Yeah? Okay, we are with the chair conformation. Take a look at cyclohexane. When you rotate, do you see what's happening when you rotate? What's happening? Is this eclipsed? What is it? Skewed? Is that about 60 degrees? Wouldn't you say that's about 60 degrees? This is staggered. There's 1, 2, 3, 4 hydrogens, and these two groups are gauche to one another, right? They were like 60 degrees to one another. This is the most stable conformation. The most stable conformation of a cyclohexane is in the chair. Wait, let me draw this back. Go back, come on now, this is taking too long for my spirit. Okay, so there they are, that's called staggered. And it's gauche. And we want to draw the chair because right now this is just starting to look to me like an olive party. I have my pimento and my jalapenos that have become my most favorite olives. So the reason why I don't have 100,000 is because I pay a lot of money for jalapeno olives. That's the truth. Huh? Let's draw. Let's go ahead and draw. So thankfully, I have this beautiful template so that we can really get this looking beautiful. So I'm gonna draw my chair with my beautiful template. I hope you can do the best you can as you try to draw your chair. I'm not gonna freehand it because this one time I really want amazing good notes. So there's my chair. And my chair has positions that are really, really important, okay? So I have, okay, with each carbon there are 2 positions. The easiest way to begin is with the axial positions. Axial positions are coming in red. That was my pimento olives on the Chem TV. And coming in red looks like this, right? So we're gonna start out, any one carbon, you can start on any one carbon. But the axial positions go straight up. So if that one is straight up, you alternate. The other carbon will be straight down. So straight up, straight down, straight up and straight down your axial positions. So if you're down, over here this guy will be up, and this guy will be down. And this one will be up, and this one will be down. So how many axial positions do you have in cyclohexane? 6. There are 6. Okay, so there are 6 axial positions in cyclohexane. There are 6 other positions that are coming in a different color. These are my jalapeno, and they're called equatorial positions. Okay, and what we do again is we alternate. If axial was up, equatorial is down and is down at an angle. And they are super strict at how you position your angling, okay? If you are down, your equatorial is up and again at an angle. Okay, so that's your up and down. When you get over here to where you're laying on the chair, they're even more strict. That equatorial is going with the slope of the line. So since the line is sloping to the left, your equatorial has to slope to the left. Meaning if you draw it pointing to the other way, it will be marked wrong. Okay, so it's going with the slope of the line. If your axial is down, your equatorial is up at an angle. Axial is up, equatorial is down at an angle. And the very last one that they ding you on, if axial was down, equatorial is up at the angle with the sloping of the line. Okay, so each carbon has an axial and an equatorial position. So each of them have these two positions, okay, axial and equatorial. So we're gonna continue on with ChemTV. ChemTV does a pretty good job. We'll continue on with ChemTV. And so they show it like that. All right, and we continue with this. And there they are, space filled, your axial and your equatorial. When you come on Monday and I still don't know what we're doing, so come prepared to do everything. Because one of the things that I really believe we need to do is we need to be able to build these molecules, and you can see that your axials are straight up and straight down. I mean, you need to like really see it. So my axials are straight up and straight down, you can see well. You can see that there are 6 up and 6 down, 3 up and 3 down. And then take a look at the green ones, right? The green ones are either up pointing to the equator or down pointing to the equator. Can you see the chair? I mean, if you don't look at the green, if you kind of wink and just look at the black, are you able to see it or kind of? Okay, you will build it so you can trust me and get it, okay? And you'll be able to see that to get from one chair to the other, right, we're gonna have to do some twist and turn. So we probably will spend some time with this in the lab on Monday. So come and bring your gear for lab notebook, open mind that if I believe people are stuck with this, we'll have to build them. It's the only way to really, really see it, okay? What happened? Huh?
When are you collecting that lab notebooks?
Monday, I suppose.
Monday?
Yeah.
Okay.
Not today, next Monday, yes, thank you. I'll send an email for that.
Okay.
All right, so we'll collect it, I'm already collecting them. All right, so we continue on with this, and here's the boat conformation. They call this a boat conformation. Look what happens as you do your boat from that chair. So it's like you took that chair like this, right? You're taking the chair like this, and you're doing like that. So you're doing that twist to get to a boat. And you can see that it happens, right? You can see that that happens, that you can get to the boat. In the boat conformation, and I'm glad you're probably drawing because I have to get to a slide. So you keep drawing for your boat as I get to the slide that I need to get to. I almost am there. All right, so my boat conformation, as I get to it, oh my goodness, I'm almost there. All right, so your boat conformation has this other problem, that you have now these 2 hydrogens that are kind of like in your steric strain space, right? So they're like in your space. Those hydrogens get a special name. They're called flagpole. And somebody took the time to show you that if you rotate, see why the boat is not as stable? Can you see why the boat is not as stable? You're eclipsing all your hydrogens from each other, right? So the idea between that cyclohexane chair that is staggered gauche to the boat that is eclipsed, as we knew, the eclipsing has that high torsional strain. Somebody took the time, hopefully everybody, there's the flagpole hydrogens, so there they are, your flagpole hydrogens. Someone took the time to measure the difference in energy, okay? And they found that the energy difference is about 6.5 kilocalories per mole. Again, I don't memorize the numbers, I'll tell you what I memorized shortly. But again, based on just the eclipsing to stagger, is that we know that it's going to be higher in energy in the boat than in that chair conformation. They continue on and they said, oh, well, take a look at a twist boat. Okay, take a look at a twist boat. If we start out with the boat and we twist, and yeah, the only thing I can really draw well actually is the boat, and they're comparing them. So when we compare the boat and the twist boat, what we see is this, that from your boat to the twist boat, seriously, this is the only place I can be here somewhere. Is everybody that I can be here somewhere? That I have deviated from the eclipsing, right? So a twist boat is not eclipsed, so you would expect that the twist boat conformation will be lower in energy than the boat conformation. All that we're doing are called conformations of cyclohexane. And your book, and the people that will be teaching this class someplace else will have this shown like this. This is how your table looks in your book. Frankly, that's my own drawing because I'm not gonna memorize this whole thing. So I'm just gonna memorize half the table, right? Can you see half the table? Because the other half will be identical. The lowest in energy is the chair, and you can go from one chair conformation till the next. Did you see what happens to go from one chair conformation till the next? In one chair conformation, that one carbon, that I'm gonna call it one carbon, that one carbon can be pointing down, and after I go all the twists, turns, and whatever, that one carbon can be pointing up. Sorry, I do not know which one's pointing up or pointing down. Okay, I can just track it here. I cannot draw. So I'm not really worried too much about you not able to draw either. But I know that the highest in energy is the half chair. Is everybody seeing that the highest in energy is the half chair? Then what? If you're going from high to low, highest conformation of cyclohexane to low. What's the highest to low conformation? Looking at your graph, high to low, energy. Going there. So the highest conformations of cyclohexane, oh, this doesn't write. Your conformations of cyclohexanes, the highest in energy is gonna be the half chair, right? Then is the boat, then is the twist boat, then is the chair. Okay, and it looks exactly the same way, one way or the other, right? It's looking the exact same way, one way or the other. The most important thing is that the lowest will be your chair, right? The lowest is your chair. So you're going through, you're going through. If you start with a chair, right? If you start with a chair, to get to the twist boat, you're going from a chair to a half chair, to the twist boat, to the boat. And I know that there are many test questions that they have you memorizing this whole thing. So, all right, so I'm moving on. Back again with my famous Chem TV. Here we go. All right, so somebody again took the energy diagram. We already saw it over there. And I'm moving on, and let's take a look at the monosubstituted cyclohexanes. Okay, monosubstituted cyclohexanes, it goes without saying, right? That you're gonna have them, which positions? In a monosubstituted, what are you gonna do?
Axial equal.
They're either gonna be on the axial, or they're gonna be on an equatorial, right? Sorry, bad segue. If you have a monosubstituted chair, that means that you've taken one of these hydrogens and you've put someone in its place. It could be a chlorine, it could be a bromine, it could be a methyl, it can be anybody. Just one. If you just take one of them away, it makes sense that that one could be either on the axial position or it could be on the equatorial position. That's what the little Chem TV is trying for you to see, right? So I'm gonna be able to have either one of those two positions.
Just replacing it with any other atom.
Replacing with any other hydrogen. The chair remains a chair, so you're not touching your carbons, right? You're not touching your carbons. If this is a cyclohexane, what we haven't drawn are all the hydrogens, right? Is everybody okay? There's obviously 12 hydrogens in here that I did not draw. So to be a monosubstituted, you're taking a hydrogen off and replacing it with somebody else. All right, so let's take a look. When I come over here, and we have now the green color is usually a chlorine, but, so I am able to rotate that chair. Right now it's looking like it's axial, right? That chlorine is pointing up, it looks like it's axial, and I start rotating the chair. And I rotate half chair. They swallowed the twist boat, but anyway, so that's the boat. To go to another twist boat, to the half chair, to the other chair, and now that one goes to equatorial. So you are able to start out with one chair on the axial position, and after you do all of the rotations, that substituent can end up on an equatorial position. So you really can have axial and equatorial positions. After that, somebody puts them side by side. And those of you that come from that really big background of that, what does that mean? What did all that mean, those arrows? What did that represent in that other class of yours? Anytime you had two arrows that represented equilibrium, you go from here to there and back and forth, the fact that you have a heavier arrow than the other, what did that mean? At equilibrium, what happened? Okay, Dean, you wanted to say?
Oh, I was just gonna say that actually.
What she was saying. Okay, so at equilibrium, what this is saying is that at equilibrium, the majority of the molecules will be in this conformation, or that the equatorial conformation is favored at equilibrium, right? That's what that really means, that is favored at equilibrium. They continue on because that wasn't enough and somebody measured delta G. What is delta G? Gibbs free energy and represented what?
Spontaneous reaction.
So yesterday I heard all about the formula. Oh, delta G was delta H minus T delta S. Oh, delta H is enthalpy, which was heat, great. Delta S was entropy, which is random, it's fabulous. I don't care about anything else. All I care is that if it's a negative value, it's gonna be spontaneous. That's all we organic chemistry care for. Somebody calculated it, I don't care how they did it, what the number was, I just care qualitatively what it means. It's spontaneous. That equatorial position is spontaneous. And so if they said to you, this is how this translates to organic chemistry. If somebody say, draw the most stable conformation of methyl cyclohexane, you have to draw it in a chair and you're putting the methyl on the equatorial position. That's English for us. So all of that, that's what that means. Is everybody? Do I need to say this again slower? Somebody said draw the most stable conformation of methyl cyclohexane. You have to draw the methyl on that equatorial position. Okay, that's what they really are asking you to do. It's on equatorial position. Based on the delta G value and based on the energy differential between the two. Let's take a look at something else. So we continue on, and there's 95%. For more of you, 95% of the molecules will be in that equatorial position. That is called stable in this class. So that number gets translated as stable for us, okay? I know that many of you are as artistically challenged as I am. So what I've done in the past is to really draw the cyclohexane chair so that all you would have to do is draw the axials and the equatorial. That way you don't come and argue, well, this was my chair, but it really does look like a, who knows what, like how I would draw it. All right, so there's again your methyl cyclohexane. Well, why is that? Right, we're saying it's the most stable. There was evidence of equilibrium. There was evidence of a delta G. And then we have to come up with a story. Is everybody there? So organic chemists find every evidence there is, all the math in the world, and then we want the story. And the story goes like this. When you are in that axial position, see how you have that axial position? In that axial position, we call that, you see me rotate that one with the axial, we see that? Okay, that we call a 1-3, okay, do it, a 1-3 diaxial interactions. I'll show you something so that you can see better. Okay, remember these were the axial positions again? These are the axials. Do you see how the equatorials, there's nobody around it? Do you see there's like no one around? Kinda like, I'm pointing out there, there's nobody around it. If I switch one of these guys for a bigger guy, like this, take a look at what happens now with these axial positions. You see this? Okay, that's what we're trying to prevent, right? You're trying to prevent that. That's a 1-3 diaxial. I can go 1-3 that way or 1-3 that way. If you switch this to the equatorial position, take a look. And I don't want to do the ring flip because it takes forever, but take a look. You see that really you can rotate freely? Okay, that's what we call stable. We don't remember the 5.1, the 6.7, the delta G. We're just saying it's more stable because you don't have a steric strain. And that particular steric strain is called your 1-3 diaxial position. Okay, so every time they want you to draw the most stable chair has the group on the equatorial position. Okay, as the groups, there we go, you see it is gauche, while over here is no gauche. Gauche, no gauche. All right. Yep, the same thing. So it doesn't matter what carbon you're using to represent an equatorial, they will all be the same. So all the equatorial positions are the same. All right, I want to go to something else, and I want to kind of, the bigger the group, the more important it is that you are in that equatorial position. Okay, the bigger the group, the more important it is that you're in that equatorial position. I'm going to draw. I don't know what else they're having here to do. Oh my gosh. All right. So I don't know what else they have, but not enough. I'm helping you with some of the homework. There is some of the homework where we're looking at a di-substituted. So we want to look at di-substituted cyclohexane. What is this? I'm seemingly like a yellow line. Do you see a yellow line?
Yeah.
All right. So let's take a look at di-substituted cyclohexane. So di-substituted cyclohexane. And I'm really looking at a comparison of a 1,2 dibromos. So let's take a look at 1,2 dibromos. And I'm going to draw my chair. And I'm going to draw my chair now pointing in another direction. Okay, so there's the chair pointing in a different direction. And for the 1,2 dibromo, right, you would expect the 1,2 to have the cis and trans, right? So I want to start with a cis 1,2, all right? So we're looking, wait, that doesn't look right. Hold on. I'm going to call this cis 1,2, all right? So in my cis 1,2, I'm going to do axial, down, and up. So your axial positions are 1 and up. Will cis have them in the axials? Will cis 1,2 have the attachments on axial? No, because they're going in opposite direction, right? So axial's up, equatorial is down. Axial is down, equatorial is up. So I'm really just concentrated on this side of my chair. It's everybody. So if I'm just concentrating on that side of the chair, I don't have to draw all the axials equatorial, there's no need for that. I'm just concentrating on the 1, 2, okay? So my options for the 1, 2 cis, the options for the 1, 2 cis is if I put the bromo on that axial or in this equatorial, right? They're both pointing up. Or they would both be pointing down. Is everybody with me? They're both pointing up in the same direction of the chair, both pointing in the same direction, both pointing up. And at this moment, oh, you're gonna come here and say, oh, wait. So I have a bromo on an axial, and I have a bromo on an equatorial position. And because you're not gifted in drawing, and drawing takes a lot of time, and people that are perfectionists, like I tend to be, I'm not gonna stop till that chair looks perfect. You don't want to waste all that time. If you were to do a ring flip, the position that was axial now became equatorial, and the one that was equatorial now became axial. Okay, and that's all we want you to do, okay? So in your cis 1, 2, one chair would have a bromo axial equatorial, and when you did the ring flip, that will become equatorial axial. Is everybody with me? Is there a difference in the energy of this chair? If the groups are the same, there's absolutely no difference. Is everybody okay? Okay, you do trans by yourself. Tell me what's gonna happen if you're in a trans 1, 2. I'll erase my bromos. You're doing your trans 1, 2. Tell me what you think you're gonna have if it's a trans 1, 2. What are the positions that you're gonna get in a trans 1, 2?
Axial, axial, equatorial, equatorial.
You're gonna have axial, axial, he says. Is everybody seeing that? You're gonna have them axial, axial, or you're gonna have them equatorial, equatorial. Everybody okay? If somebody said, are we all okay? I mean, do you have any questions? It's really important that you understand this, because you're gonna do all the cis 1-3, the trans 1-3, the cis 1-4, the trans 1-4, and this is the typical questions on exam that people go, I never got it, this is your time, okay? Well, we're gonna build them on Monday still. Everybody knows what we're doing, right? We're putting them, you can start out for the trans, that they're in opposite end, so your bromo is up and down. That's trans and opposite. So that's how we started with the axial, axial. When you do the ring flip, if you were able to do all the drawings, then you would end up in equatorial, equatorial. Here are some of the questions. In the trans 1, 2, is there one chair conformation that is more stable than the other?
Yeah.
Is everybody seeing? This one, equatorial, equatorial. The trans 1, 2, equatorial, equatorial is the more stable conformation than the trans 1, 2 when they are axial, axial. Based on, you're gonna have 1, 3 diaxials at the top, and you're gonna have 1, 3 diaxials at the bottom, right? Because you're gonna have a bromo up here doing that, you're gonna have a bromo down here doing that as well. So the axial, axial with the dibromos, very unstable. Like you will not see any. 95% of the molecules are gonna be on the equatorial, equatorial. Opposite to that story, when you're looking at the cis 1, 2, it doesn't make a difference if the groups are the same size. Same, you have 1, 3 at the top, or you can have 1, 3 at the bottom. So it doesn't make a difference. But if the question was of the geometric isomers of 1, 2, geometric isomers of 1, 2, is there one geometric isomer that will be more stable than the other? Well, yes, the trans. It's everybody. So the trans geometric isomer of 1, 2 is more stable than the cis because you will have your groups in equatorial. So this here is what you're going to use to finish that discussion packet. There's a big portion of the discussion packet that looks like this. That is what you're gonna wanna go ahead and finish. Where is that yellow coming from? It's driving me crazy. It's totally driving me crazy, this whole yellow band that I see right there. Okay, huh? I don't know what it's looking at. All right, better than that. Okay, so those are your cyclohexane chairs. Okay, so you want to go ahead and draw. Can you draw? You're drawing? All right. So you're going to draw. I have such a mess of papers. Draw the most stable I'm thinking on the fly, I'm not doing too well. 1, 2, 3, trichlorocyclohexane. Draw the most stable. 1, 2, 3, trichlorocyclohexane. I'm going to attempt to freehand my chair. I can freehand the chair. And so you will do axial, and it doesn't matter where you start. Axial's up, axial's down, axial's up, right? Doesn't matter where you start, I chose to start here. Axial up, axial down, axial up. Equatorial down, equatorial up, equatorial down. If they don't give you anything and they say draws 1, 2, 3 trichloro, what are you gonna do? I guess I'm gonna put the chloro there, the chloro there, the chloro there. Yes? And oftentimes what you're gonna have is they're gonna draw the hydrogens, hydrogens, hydrogen. So that's one way of doing it. Or if you, once you have done that like so, sometimes no two chairs are alike. Did you notice that? No two chairs are alike. If you don't want to do the up and down, then the other way that you can do them is you draw them like so. And then you put your chlorines there. So if you do up and down, if you're doing up and down, you have to leave the hydrogens on there. If you don't want to do the up and down and you just want to represent it, then don't put the axials, okay? These are the only two acceptable drawings on that. There are only two acceptable drawings, and if it is, usually what I do is I start with my up and down so that I know where I'm going to do them, and then I will represent them like that, okay? Is everybody okay? Mm-hmm. All right. I think this is really the end of the chapter. I really think there is no more to this chapter, and they do it all. Okay, one moment, people are already talking. Hold it, don't leave me. So this is, oh, you didn't want me to see the function 8 anymore, right? So from here, if you're looking at that table where we were at this table, so we were at this table, they really are doing the exact same thing. They're having just everything that we've talked about, everything that we have talked about with the ChemTV, you know, the tert-butyl, most strongly preferred, the cis-1,3, so you'll see it all there. So it's all that we've been talking about in the discussion packet. And then I really think we are done. So everybody, you are done. So we have covered everything in the chapter. So when I see you again,